So let's talk about the concept of a bridge. We'll start with these two simple circuits. We have some resistor and some unknown, and if we have a circuit that we don't understand, we could make another circuit that we do understand. So we could have the same R on the top, and then we could have some type of variable resistor on the bottom. And if we come here and we measure this voltage, and we get some value, we could then go to this circuit, we could measure this with this voltage, and then we could change this resistor on the bottom until we got the same voltage that we got over here. And then we can say, well, these circuits are similar, and so whatever this is, that must be this. And so if you know what this is, then you know what this is. And that's the idea of using two things and trying to make them equal, and then if you know these things, then you know these things. All right, so that's a concept. And we're going to take that exact circuit, but we're going to draw it differently. And so we're going to draw it like this. So this is the bridge that you generally see in electronics. And sorry, my camera is off a little bit there. There we go. And so this is the circuit that we had before, resistor and unknown. And this is the circuit that we had before, resistor and some way of changing the value of this one. And then we're going to measure these 2 points. And if they're the same, then we're going to measure 0 volts. If this is a voltmeter, then we're going to measure 0 volts between these 2 points, because whatever voltage here is the same as here. So if you had a voltmeter in here and you kept adjusting this potentiometer until you read 0 volts, then you could safely assume that this is the same resistance as this. And if you think about this circuit, you could also say, well, if we have some voltage flowing in this thing from, say, top to bottom, it gets split and it comes together. And there's a current in each of these legs, an equal current in each of these legs. And if they're unbalanced, then there's a little bit of current that might go across the center if that was possible. A voltmeter won't allow current to pass, but what if this is an ammeter? If this is an ammeter, then any unbalance in this circuit will cause a current flow in here as well. So a lot of bridge circuits that you see, especially from the old days, they'll have a circuit just like this, and they'll put a microammeter, an actual physical meter. And again, you can change it so you get 0 in the center. Now, the nice thing about ammeters is a lot of times you can get 0 center ammeters. They'll measure negative current in one direction, and they'll measure positive current in the other direction. So if this thing is unbalanced in one direction, it'll go that way, and it may unbalance the other direction, it'll go that way. It's hard to get a center voltmeter that goes in both directions. All right, so if we go another step, we might see a circuit that looks like this. You might find this one where there's 3 resistors, and we're going to measure the voltages here. And you can imagine maybe having this resistor is because we want to measure the current, and voltage across the resistor is a measurement of current. And so you might put a large resistance value in the center to not disturb the bridge. This is called the bridge. Not disturb the bridge, but allow you to measure current in the center. The other reason that you might do this is to equalize the power. So a lot of times a power splitter, you can have 2 resistors as a power splitter, or you can have this triangle as a power splitter, and it just makes it more uniform and equal. So you could use this as well. So instead of talking too much about this, let's build one. This is a simple bridge. We're going to have 4 resistors, and they're all going to be the same value. So 1K, 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 and 1K. we're going to connect the top to a waveform generator. Okay. We're going to put a waveform generator in the top. And then we're going to hook this up to an oscilloscope. We're going to have channel 1 looking at this side. We're going to have channel 2 looking at this side. So hopefully we'll see the exact same signal over here and over here. Now over here we'll see half of the voltage. So if this was 1 volt peak to peak, we'd see a half a volt peak to peak here. And the same thing over here. Let's wire up the circuit, take a look. All right, here we have our 4 resistors and our function generator coming in the top, ground at the bottom, and we have channel 1 over here and channel 2 over here. And if we move one of these down, you can see channel 1 and channel 2 are exactly the same, and they lay right on top of one another. All right, so let's come out here. Maybe you can see a little bit better, but they're basically the same. They're a little bit different. There's the 1K resistors are going to have some tolerance to them, so they might be a little bit of difference, but basically they're the same. All right. So if we change the resistance of one of those resistors, so this resistor here, okay, I'm going to put another 1K resistor in parallel with it. So I'm going to have half of the resistance in that one. So I'm going to change this. I'm going to put a 1K resistor in parallel with it. So now we'll have 500 ohms in this part of the bridge. And you can see the channel 0 got smaller. That's because 500 ohms is smaller, and there'll be a smaller voltage on that side. All right, so that makes sense. And if we put the two in parallel, not in parallel, and they're in parallel now, if we put them in series, then we would have a larger voltage than channel 1. I think that's self-evident. All right, so let's do something a bit strange now. Let's put a capacitor in parallel with that 1K resistor. All right, let's see what that looks like. All right, I'm going to take out the 1K resistor, and I'm going to find a capacitor, and I'm going to put that capacitor in parallel with the 1K, and let's see here. There we go. All right. So what happened? Well, the voltage didn't change much, but something else did change. The phase changed. Okay, so the signal moved over. So channel 1 stayed put, but channel 2 went that way. So I wonder why that. I wonder why there's a phase change. All right. So before we talk about it, let's do one more experiment. And this time, we're going to put an inductor across the 1K resistor. All right, we'll put in a 10 microhenry. So we'll take out the capacitor, and we will put in 10 microhenries. And what happened? We got about the same amplitude. We got a phase change, but this time it shifted left. So now it comes before. All right, when I was a teenager, first learning electronics, it was because of ham radio and the ARRL radio handbook. And I remember there was a couple things I learned it very early on. One was E equals IR, voltage equals current times resistance. The other one was Eli the Iceman. I think every kid remembers Eli the Iceman. I knew what it stood for. I didn't really understand it, but I knew what it stood for. That in an inductor, the L is in the middle, inductor, and the ice is C is in the capacitor. So in Eli the Iceman, the voltage comes before the current. So voltage leads current, a current lags voltage. And in ice, current leads voltage, voltage lags current. And I knew that. Didn't really quite comprehend the usefulness of it, but I think you needed it to pass the test, or I don't know, or maybe it just stuck in my head. I don't know. Anyway, Eli the Iceman. Anyway, we saw that in the scope. So we saw when we had a capacitor or inductor, the phase shifted, and so we've seen that. So there are a couple instruments that were made around that idea. One was a vector voltmeter. You don't see them anymore, but you did back in the day. And a vector voltmeter would measure both amplitude and phase, would actually give you a phase angle. So you could use a vector voltmeter in networks, and then you could actually do a bunch of math yourself and do scatter parameters, S11, S12, that kind of thing. So you were your own VNA. It wasn't until some time later that somebody came out and put it all into one box and did a bunch of stuff with it, and made vector network analyzers. The other place that it was used was in LCR meters. Probably if you look at something like this, LCR meter, you'll probably find that there's some math in there that looks similar to Eli the Iceman. All right, so we looked at bridge circuits, and here's a bridge circuit with a center resistor. And this is the circuit that's in the NANOVNA. So inside the NANOVNA is a bridge circuit with one of those resistors across. Now this is on channel 0. So channel 0 is an SMA connector on the side of the top of the instrument. And if you think about putting a resistor out here to ground, it's this ground and this ground are the same, so that resistor actually is like being in here. So anything you put on the outside kind of appears in this fourth leg of the bridge. Okay, so I've kind of put that in dotted lines, so things on the outside there really are in the bridge circuit. So that's what channel 0 looks like. So what does the NANOVNA have in it? Well, it has an RF generator, a little DDS chip. And the first thing that happens to that generated frequency of interest is it goes through a power divider. And so some of the power snakes off over here and some of the power goes off over here. This power is going to be used in the bridge circuit. This little power here is a little tap, and we're going to measure it. A prime, B prime, and C prime are the measurement points. So there's three measurement points in what I've drawn here. So, like I said, a certain portion of the power, like 10% of the power, comes off over here, so we can measure it, and then the rest of the power comes down here to be used, and it goes through this bridge circuit. So channel 0 goes out, and whatever unknown you connect to the channel 0, it appears here in this bridge. And then we need to go measure the voltage and phase across this bridge circuit. All right, so what does channel 1 do? Channel 1 is input only. And so you need to input a signal here. It goes through an attenuation pad and then is measured, right? So there's 3 measurements, 2 channels, and we measure the incoming RF, so we know its amplitude and we know its phase coming in. Then it goes through the bridge circuit, and we know its resulting amplitude and its resulting phase. And then if that goes out and goes through some network and comes back into channel 1, we then know its amplitude and its phase. So we have these 3 things. And once we have these 3 things, then we just run into a whole bunch of mathematics, and poof, out pops everything that we need to know. So this is the VNA. This is all there is to a VNA, these 3 things, all right? So how do we measure these 3 things? That's the real key. We know we want to measure them, but how do we measure them? Well, we could get a nice expensive oscilloscope and 3 channels, and then we could digitize those, and we could send it to some software, and you might spend a lot of money doing that. So how can you do that cheaply? Well, one of the problems is, how do you measure up to a gigahertz cheaply? It's maybe easier to measure, like DC voltages is easy. Maybe some really slow AC voltages are easy, but 1 gigahertz is not easy. So how does the NANOVNA do that? Well, way back when, a German ham, I'm trying to remember his call sign, DG6SAQ, I think that might be right. I'll try to find his paper and link it. He said, you know, I think we can build little cheapy VNAs. We can do this thing, and then we can use a certain thing, and I think we can do it pretty cheap. And those were manufactured. Those were called like the MiniVNA, and they were like $500 and required you to have a PC. But his idea was, let's go ahead and take those things we want to measure, A prime, B prime, C prime. So these are differential pairs here. And we want to measure these 3 things, but they're too high in frequency. So every RF engineer knows, well, if it's too high in frequency, you can always put it through a mixer and make it a lower frequency. So that's what this does here. There's 1 master clock, and it comes in, and it runs through these 3 mixers, and it takes whatever you have, let's say it's 1 gigahertz, and it's going to mix it with something, and it's going to end up at audio frequency. So let's say 10 kilohertz is a good frequency for you. So you have 1 gigahertz plus 10, 1 gigahertz plus 10 kilohertz, and when you mix 1 kilohertz plus 10 kilohertz to 1 gigahertz, it mixes down to 10 kilohertz, right? And so I don't know if they use the plus or the minus, but it's when you mix these 2, you end up in audio land. And if you end up in audio land, these are just RF filters, so noise doesn't filter into your audio frequency. All this RF doesn't make it into your audio stuff. That's all this stuff here is. And then you can put it into an audio A to D. What is an audio A to D? Well, that's a sound card. So back in the day, the original idea was to use a PC sound card, and you would just run this into a sound card, you'd digitize it, and then you would do a bunch of math on it. The little NANOVNA basically uses a sound card on a chip, and so this is all just 1 chip. It's a 3-channel chip, and we can measure those things, A, B, and C. So that's what that is. So what is all the stuff about calibration? Okay, so now that we have, where's my drawing? This is good. Now that we have the hardware to do the measurements, and now that we've made the measurements, we need to run that into software. And the software needs to know some things. It needs to be calibrated. How do you calibrate amplitude, and how do you calibrate phase? Okay, those are the 2 things you need to calibrate. All right, so we're going to use these 3 things, open, short, load, to do the calibration. Now, why are these chosen? Well, a open will allow you to measure phase of the known type. If you have an open, you know the phase is 0. If you send something down a transmission line and it reflects off of nothing and it comes back, it's in phase. If you have a short and you send a signal down a transmission line and it sees a dead short, it comes back out of phase, 180 degrees out of phase. Okay? And so we need to create some type of calibration standard. I have a video showing me constructing this set of cal standards as an open short load in female SMAs. The ones that you get in the kit are male, but sometimes you want to be able to calibrate with females. And so I constructed these, and I'll show you my thought process and why I did what I did to make these things. So these are cross sections of the little SMA connector blown up. And so we take one of those connectors, and we basically, there's nothing on the back side. So if you looked in this, you would just see a center conductor, and then you would see a plastic insulator, and then the rest would be metal. All right, that's what you would see here. And so I just made sure this was all flush, and that's my open. So the electrical signal will come down the center conductor, the pin, and it will come to here, and then it'll see nothing, and then it'll go right back the way it came, and it'll stay in phase. Right? So that's the open. The open is really, really easy to make. Now, what does that mean? It means that there is some place where phase is 0. And that place is right where this reflection happened. So we're going to call that the reference plane. Okay? So right here is the reference plane. Okay, so now we want to make a short. We want to make a cal short. The cal short has to have the exact same reference plane. All right, so there's a little piece of copper put here, and it was soldered in place, so now everything's shorted together, and when the electrical signal comes down, it sees the short and it reflects back out of phase. But where does it reflect? Right at this plane, at the reference plane. And then putting it in two 100 ohm resistors, I tried to keep them exactly on the reference plane. I'll let you think about whether it's important to preserve the reference plane in the load or not. I'm not sure how much phase information is actually taken from the load calibration. And if you think about the cal standards you were given, I think you can convince yourself that the open and the short have similar reference planes, but the actual load does not have the same reference plane, so I'll let you think about that. But this is basically the idea. There is some reference plane. Now, if you get a $100,000 40 gigahertz VNA, you're talking like $4,000 or something just for the cal standards. They're machined very, very accurately to have exact mechanical phase planes, these reference planes. And that's a big trick. The connectors on the front of the instrument are super, super expensive. The equipment inside is super, super expensive to make sure that these reference planes are held really, really close. Now in the little NANOVNA, we're holding them within maybe a few picoseconds, but in a big VNA, you have to be much, much better than that. Okay. So, what else is inside these NANOVNAs? Okay, so I drew the kind of the poor man's version of these schematics, but what are the actual values used in these things? Here are the three mixers. Here's the sound card chip. So the three mixers. Here's the oscillator. So the oscillator feeds these three all in phase. They're all mixed exactly in phase, and the sound card has a reference signal coming from that as well. All right. So what do we have here? We have those three things. We have the power splitter. We want to measure the power. We have the bridge, and then we have channel 1. All right. Now I have two schematics. I have a schematic for the original NANOVNA Rev 3.0, and I have a schematic for the NANOVNA H4. So a lot of people are going to be asking, what is the difference between the Nano and the Nano H4? Is there any difference in hardware? So this is what I came up with. On the left-hand side is the NANOVNA, and on the right-hand side is the NANOVNA H4. All right. So in the NANOVNA, make sure I'm on screen here. In the NANOVNA, there's a power splitter, 470 ohms to 27, and it's measured, and then 150 to 56, and it's measured. And so if you do the calculation, which I don't have in front of me any longer, let's see here. Oh, now I've lost the calculation. But it's something like 10%. Something like 10% if it goes this way. You could do the calculation. It's real easy to do. All right, so it comes down here to the bridge. The bridge is 49.9, 49.9, 49.9, and the unknown. And then there's an 82 ohm resistor across the two, right? And then we want to measure A prime, B prime. And then the channel 1 comes into a isolation pad, attenuation, 100 ohms, 39, 39, 22. 39 plus 22 plus 39 is 100. So 100 in parallel with 100 is 50. So the input impedance of this thing is 50 ohms. And then the output is something lower than 22, maybe 19 ohms or something like that going in the other direction. And the amount of attenuation is, in this case, you couple about 22%. 22% of the signal comes to CC prime. Now, in the NANOVNA 4, H4, they've changed the power splitter. They've left the tap to measure amplitude the same, but they've got rid of that 150 ohm resistor and they put in a 0. So they're coupling a lot more power into the bridge. I believe they probably did that because they're going to use one extra harmonic and they needed more power. And so they did that to increase the power into the bridge. So the bridge stayed the same, 49, 49, 49. But they did change the pad. The pad now is 91, 51, 51, and 11. And so the input impedance to this thing is now no longer 50 ohms. It's now 101 ohms. Looking in the connector, it's 101 ohms. And then looking back this direction, it's right around 11, 10 and a half. And we're coupling out about 9.7%. All right, so 9.7% is coming out here, whereas 22% is coming in here. So I think that was done because we have lots more signal coming out. We have lots more power coming in here, which means if we go from channel 0 to channel 1, we would overdrive the sound chip, and so we needed to lower that value, and so that's why they changed this this input pad. All right. Wow. Okay. So I hope you enjoyed that. I hope you followed most of that. It's a pretty simple circuit on the surface. Most of the tricky parts is going to be the mathematics of this whole thing, the calibration of it, the use of harmonics is a big deal. But the underlying theme here is that it is pretty simple, and you can see how being used as an antenna analyzer, you're really just putting your antenna into a bridge, and then you're seeing whether that's 50 ohms or not. Then the bridge will balance. And if there's any phase shifts, either positive or negative, you have positive phase shifts, you move up the Smith chart. Negative phase shifts, you move down the Smith chart. Hope that all makes sense.